So it's really, thank you. Sorry. It's really with a great pleasure to introduce you to Associate Professor Zhaolin Chen. He's really a distinguished researcher at the Monash Biomedical Imaging Lab of Monash University in Melbourne. So he specializes in medical imaging and machine learning, and he has really made significant contributions to this field, including actually leading this establishment of the first Australian point-of-care MRI network, really together with Professor Meng Law and Professor Paul Parizel. And he has secured over more than $8 million as well in research funding to really conduct these studies. And today he will be giving an overview of ultra-low field MRI. Thank you.
Well, thank you, Karen. It's a really powerful patient's story. So my background is engineering. I'm going to talk about the ultra-low field from an engineering perspective. What is the current development? What are the limitations and challenges around the ultra-low field? So I just want to be a little bit more clear that the ultra-low field we're referring to in this session was a 10 to 100 millitesla MRI. So this is a fast evolving field, right? The definition for ultra-low field, a very low field, is a bit changing. It's like how we define high field, ultra high field now. So there was a 2023 SMM workshop that it refers to, can't really see it here, the low field from 10 millitesla to 100 millitesla. There's a subsequent study published in JMRI. It refers to 10 millitesla or 100 millitesla is a very low field. There's a recent study by the Unity group. So they actually do a multi-site study on the calibration for the ultra-low field, so at 64 millitesla, and they refer as an ultra-low field. So just to be clear through my presentation, I'm referring to ultra-low field in specific from 10 millitesla to 100 millitesla. So just adding a little bit more historical background, MRI start with a very low field to begin with. So late 70s, early 80s, the first home-built system is always below 100 millitesla. But things changed very quickly in early 80s. So the first commercial system is already 0.5 Tesla. And since the introduction of the 1.5 Tesla scanner, so all the ultra-low field, the low field is gone, right? It's a wall of the field strengths. Since then, 3 Tesla, 7 Tesla, 9.4, 11, 14. So it's been changing dramatically with the field strengths because of the drive for SNR resolution and the clarity of the images. There's a recent change, as you heard from Karen's talk, the accessibility was one of the major drivers to reduce the field strength back to millitesla. So there's a number of homemade systems around 50 millitesla now, and there are commercial systems now at 50 millitesla, 64 millitesla, and so on. So quite a few companies now building ultra-low field scanners now. So this is a nice review paper by Jürgen Henning, really putting a little bit of historical backgrounds on the advantage of the permanent magnet for the ultra-low field and superconducting magnet. You see the names around superconducting magnets, Toshiba, now Canon, Philips, Siemens, GE. So those are the main manufacturers now for superconducting magnet. So I'm not going into details of this this paper, but if you, it's highly recommended. It's very interesting to read. So just also coming back to Karen's point on the high field MRI with ultra low field MRI. So the high field MRI, of course, is very expensive, and you have to have a large footprint and a special room of design, shielding, superconducting, and operation room, strict regulations, and of course, you take home with the advantage of being an MRI machine, right? The ultra-low field, on the other hand, is a lot cost-effective, a much smaller footprint, and patient bedside, accessible, mobile, and also you have the advantage of being non-invasive. However, the SNR and other things still require improvements. So one of the major things, challenge with ultra-low fields, of course, is SNR. So we know MR signal is proportional to the field strength squared, and the SNR, the SNR is scaled with field strength. At the ultra-low field regime, so it's proportional to be 0 to the power of 704. As a result, SNR at 64 millitesla is at least 2 orders of magnitude lower than the 3T MRI. And not only SNR, but also contrast is becoming lower. Contrast noise is a problem. So T1 is reducing compared from the low field to a high field. Although T2 remains reasonably stable, but if you look at the T2 contrast to noise, the high field has a dramatic advantage compared to low field. So both contrasts, T1 and T2 are main building blocks of MRI. The low field suffer from significant issues with dropping SNR. So this is example. You can see the 64 millitesla compared to 3T millitesla for the anatomical structure scans, T1, T2 flare. The SNR resolution is much lower, and the diffusion and the ADC maps are also in reduced quality in terms of SNR and the resolution. So this is our data set. We registered the T2, which is probably the most, the best sequence in terms of ultra-low field because of and from MR physics point of view, it's not reducing that much compared to T1. So if we register T1, the 3T, which is on the left-hand side, the ultra-low field on the right-hand side, you can still see the registration quality between the two modalities is still reasonable. Although I have to say, when we position this is the same patient, this is just a linear registration, we have to put the isocenter pretty aligned to make sure that the physical alignments of the two patients are good. Okay. So there are, of course, besides the SNR, there are a number of other challenges. One of the major ones is electromagnetic interference because unshielded environments. We have RF leakage. In room scanning, we have the lights, we'll have RF interference with the scanner. So it's always necessary to have a right location for the scanner, especially you're doing it in the lab environment compared to hospital environment, will be less of EMI. In the lab environment, you have a lot more EMI. And the geometric distortion, which is another major issue because of B0 field inhomogeneity, and the gradients, nonlinearity, eddy currents, and so on and so forth. Therefore, the processing is very important, including bias field correction. So the images showed you before was the bias field corrected. And the standardization will be more challenging on the ultra-low field due to the image quality, the size difference, but also because it's a fast evolving field, each different software version having quite different image quality. And the long scan time is another thing. And the low susceptibility weighted contrast is an advantage. We can have less metal implants, increase safety, but as a result, low susceptibility. We know bold contrast and other contrasts is quite relying on susceptibility weighted contrast. And clinical acceptance is building up. There's a lot of unknowns at this stage. So, but having said all the disadvantages, the advantages Karen mentioned before, the point of care being portable, cost-effective, accessible, and remote deployment and sustainable. The carbon footprint is much lower with the ultra-low field compared to the high field. And reduced SNR, metal implants, imaging, which could be another major opportunities there. For example, for some of the neuro intervention work. And also opportunities to use AI for ultra-low field, including field workflow optimization, image quality enhancement, and clinical decision. So this is a recent review paper. They try to summarize a number of studies using the ultra-low field, the field strengths I defined. And if you can see, the majority of the papers actually use the ICU or ED environments. And the majority of the problems they mentioned, the limitations are SNR and the motion artifacts, degraded images, so image quality related. And I'm not going to the full details of this paper, but you can see the number of studies around here are mainly around ICU implementation. There are some lab scanning as well. So I think it's great to have the variety of the setups, and that's be essential to move this forward. And also the recommendation for next steps, for example, including the resolution of images using AI, and the more data sets could be set up for the progressing of the field. So it's a very good paper to read. So now I want to switch a little bit around to the generative AI for the image quality enhancement in the field. So medical imaging generation translation is a fast evolving field. So quite a few tasks you can do now is with generative AI. So from MRI to CT translation, MRI to PET, low field to high field, T1 cross modalities, and within PET cross modalities, and the PET to CT. From model point of view, from early on, we use versional autoencoder, UNet, and cycle-consistent GAN, conditional GAN type of setup, to more recent transformers and diffusion-based models. The image quality increased quite a bit. So, and next, I want to highlight a few studies that use AI to address some of the problems I mentioned in the ultra-low field image quality. So this is a paper published by Ed Wu in University of Hong Kong in Science, where they built a whole body 50 million Tesla scanner, and they use AI to deep learning to address the EMI problem and improve the image quality. So it's quite impressive image quality they can acquire, address some of the limitations we have with the ultra-low field and generating the whole body image quality. So this is further developed within the lab, I believe, and so a few other labs are developing different field strengths, different MRI systems, and addressing more clinical focused needs. So this is quite useful tool. We've been using this. So things that are, some of you may know this, it's quite useful to improve the resolution from a low resolution inputs, and then you can do segmentation, standard segmentation, so on and so forth. This is an interesting study. It's only an archive paper. The reason I bring it up is potentially one of the areas ultra-low field can be useful. So the central idea is you can scan a high field baseline image, and then you use low field to follow up. Right? Then you can build up a prior information from the baseline high field scan to enhance the follow-up low field images while maintaining the sensitivity to detect pathology or detect biomarkers you want. So it uses AI framework to extracts personalized features from the prior scan and integrates them during the image reconstruction. So it's quite a unique way of using the ultra-low field, reducing cost, and making it more flexible for different applications. So this is a recent publication in radiology where they use pix-to-pix model, which is pixel-wise generative model, to translate 64 millitesla to 3T image using multiple sequences. And they showed the three contrast reference here, T1, T2, and the flare, and the reconstruct T1, T2 flare. So input is a 64 millitesla, and reconstruct at the high field, 3T. So their main focus application for this paper was MS. So they showed the initial 3T and the original 64 millitesla, and then the generated images and compared them side by side. So in majority of the cases, they demonstrate improved identification of the lesions using the generative AI model. So it's quite clear that the 3T has a better identification, much sharper, accurate clarity of the visualization by MS lesion compared to 64 millitesla. The generative AI improves that compared to the original 64 millitesla. And also, they highlight there are potential false negatives. For example, in 3D, for example, this area, there are two lesions where both 64 millitesla and the generative AI model miss both. So this is still a field being developed, and a lot of validation still needed for translating generative AI into clinical practice. We also, in 2023, developed a similar technique, high-low res scan, which is also a GAN model, to translate the ultra-low field to 380. So in this work, we basically use single contrast for each modality, T1 to T1, T2 to T2, flare to flare. And we demonstrate that our model with careful design of the low field, high field characteristics can outperform existing models in the literature. And in a subsequent work, we apply this to MS lesion to several pathologies within our study. So this is MS patient case. This is tumor case, where you can see that the generated images, which is the last row here, 3T is first row, the point of care MRI, which is 64 millitesla, MRI in the middle row. So the first thing I want to highlight is the 64 millitesla still identifies the MS lesion to a very good level of accuracy. Although small lesions at the subsequent analysis may be less sensitive in the 64 millitesla scan, but with the generative AI recovers the lesion using a standard segmentation technique, you can see it's much closer compared to 3T now with generative AI compared to original point of care MRI. And this is the same for the stroke patient here. We can see the point of care identifies the pathology, but have a less clear boundaries in that. So, and our generative AI technique improves that identification of the pathology. So the process. Yeah, that's all. So really acknowledge the National Imaging Facility to support our network, which runs 5 sites, a couple of hospitals, Royal Perth Hospital, Alfred Hospital, and Samurai, to collect clinical data, but also Monash University and Hurston Imaging Research Institute to collect the healthy patients in our study. And also the MRF Survivorship Care Grant led by Professor Karen Hinsberg from Deakin University will continue looking into TBI, and also thanking our partners and supporters. Thank you.
Thanks a lot for that wonderful talk, Zhaolin. Any questions from the audience? We have a few minutes for a few questions. Yeah, of course, Mike, go for it.
Thanks, Karen. Zhaolin, excellent lecture. The slide that you showed, the first scan is high field, and then the follow-up scan is low field. what is the strategy for, you're using a paired scan to detect the abnormality on the high field, and even though you don't see it on the low field follow-up scan, the GAN is actually detecting it there, and it's, even though it's not visible to the human eye, right?
Yeah, or potentially,
Yeah.
potentially, to really reduce the, so some, for example, the MS cohort, we have seen that low field perhaps a bit less sensitive to small lesions, but with a high field baseline, maybe we can maintain or increase that sensitivity to a level that is becoming standard of care MRI results. So something we can't see, as you mentioned, we can't see in human eyes, but potentially can identify it by the machine learning algorithm.
Yeah. So even though you produce the image, you will produce a report that shows that the MS lesions are the same or worse or better, even though you don't see it on the scan, right? So you already need to have that validated because there's no human to validate it after.
Yeah, I guess not seeing, well, you probably know better, me. So probably noise is, from an engineering point of view, SNI is the issue, right? So if the noise is too much, you still have a signal within, but it is undermined by the noise, then we can't see, but the signal is actually there.
Yeah, I mean,
Or partial volume effects.
yeah, I mean, ultimately, we actually don't need to generate the image. You know, we just need to generate the report.
That would be a whole different topic, whether we need the images or not.
Well, if you wait till the 4:30 lecture from me.
Directly
then
from the
yeah.
report, yeah.
I'll talk about that.
That's right.
Thanks. Any other questions, comments?
So maybe I will ask another question as well. It's about, I'm interested as well, like now that we are collaborating with a lot of clinicians, I still feel as well that there's still a lot of reluctance as well from clinicians to accept these synthetic images for diagnosis. How do you think we can improve that?
Yeah. So we start looking, I think Tohei will show some results of unsupervised learning. So there's a balance between how much image quality you want to improve and against the generalizability of the model. I think it's necessary to have unsupervised learning to support some of the generalizability combined with the power of supervised learning, where it really improves if we have confidence to improve the anatomical structure, for example, while maintaining the possibility that could be a pathology where the model didn't see. Right? So medical imaging in the end is exploratory, right? We don't know what we are looking at. Yeah. So, yeah, great question.
Any questions from the audience? Please feel free. No? Okay, let's thank Zhaolin again for this great overview.